Okay, Assalamu alaikum jami'an, and welcome to our lecture today. It's a continuation of our lectures on selected topics on radiation physics. Previous lecture, we started talking about collisions of two particles, and we looked into different scenarios based on the mass and so on. So today we're going to extend this into dealing with this topic of stopping powers. Yeah. So charged particles, the way they interact with matter is if you have an energetic charged particle traversing matter, it will undergo a Coulomb interaction with the atoms in the medium. This will be in the form of Coulomb interactions with the orbital electrons and Coulomb interaction with the atomic nuclei. So through these collisions, the charged particle may lose their kinetic energy through collisions or radiation losses, or its direction could be changed. And this is what we call scattering or elastic scattering. So interactions of charged particles can be divided into soft collisions or with interactions with the orbital electrons. This is subdivided into soft collisions and into hard collisions. And also the charged particle, they also will interact with the nucleus. So these are the three types of interactions that a charged particle may undergo with an atom. Soft collisions, remember this parameter, the impact parameter, is basically the trajectory path of the particle with respect to, let's say, the nucleus, center of the atom. So if this impact parameter is very large, it's large in comparison to the size of an atom. So A represents the radius of an atom, and B represents the impact parameter. So if B is much larger than A, then the incident charged particle will undergo soft collisions with the whole atom. This means that the charged particle is going to transfer small amounts of its kinetic energy with to these orbital electrons within the atom. So it's not so when it interacts with number of orbital electrons, and each one of these orbital electrons is just going to take a few percent of the energy from the charged particle. This is what we call soft collisions, and essentially the energy transfer to each of these orbital electrons is really small, and the orbital electrons, they don't have enough energy to form, let's say, their own trajectory, or let's say they will locally deposit their energy from the region from which they were created. This is a concept that we will deal with this at the end of this lecture, inshallah. Then we have hard collisions. This is when the impact parameter is of the order of the radius of the atom. So when the parameter approximately equals 8, then the charged particle will undergo a hard collision with a single orbital electron. When this happens, a significant amount of energy actually will be transferred to this orbital electron. So when you have a single electron here, and a hard collision happens between the charged particle and the electron, then this electron, when it moves, it will move away from the atom. It will have significant kinetic energy, and it can deposit later. It can deposit those away from the region from where it was initially generated. So this is hard collisions. And the last interaction is essentially an interaction of the charged particle with the nucleus, not with the orbital electron, but with the nucleus, essentially meaning that the impact parameter B is really small, is smaller than the atomic radius. In most cases, these interactions, so when this incident charge particle interacts with the nucleus, most of the interactions are actually going to be elastic scattering. So the charged particle will just, its a direction will be changed without really losing any of its energy to the nucleus. But in some situations, some of these interactions might be termed inelastic, where in this situation, uh, the charged particle will lose a significant amount of its energy in the form of X-rays. And this is what we call Bremsstrahlung X-rays. I think in lecture 3, we talked about production of X-rays, the Larmor relationship, and so on. So the mass stopping power, or let's talk about first the linear stopping power. Linear stopping power is defined as the rate of energy loss per unit of path length. Imagine we have a charged particle and it's moving in medium. Then we look at how much energy is lost by this charged particle to the orbital electrons, or let's say to Bremsstrahlung within a unit of path length that it traverses. This is called the linear stopping power, and it's basically dE. So this is the change of the energy of the charged particle by dx, where x is the unit length or length traversed. Then we can have the concept of a mass stopping power. We're not interested in a linear form of energy loss, but in we want to take the density into account, and the mass stopping power is given by the linear stopping power dE over dx divided by the density of medium. And of course, we're putting here the minus sign because dE, the change is actually negative. So negative with negative, then this will give me the amount of energy that is lost by the charged particle. The mass stopping power, since we have talked about the interactions and how the charged particle may lose its energy, we said this could be through soft or hard collisions with orbital electrons, or through radiative losses with the nucleus. Then we can divide the mass stopping power into two components, a collisional component and a radiative component. So the total stopping power, the total energy lost by the charged particle will be the amount of energy lost per unit density, per unit length per density through collision interactions, plus the amount that is lost through radiative interactions. So the radiation stopping power, this is Coulomb interaction between the incident charged particle and the nucleus. And this results, so whenever this interaction happens, a Coulomb interaction between the incident charged particle and the nucleus, the charged particle may be scattered with no energy loss. Actually, this maybe around 99% of the time is actually the interaction of charged particles with nucleus will be actually in the form of elastic scattering. And in this case, this is characterized by what's called an angular scattering power. I'm not going to talk about this, but it's basically, think of it as the average change in direction per unit length traverse. The charged particle, so it may also lose some of its kinetic energy in the form of Bremsstrahlung, and this is what's characterized by the radiation stopping power. Also, I think we covered when we talked about the Larmor relationship, we showed that the power radiated by charged particles, this is inversely proportional to the mass of the particle squared. So the radiation losses is inversely proportional to the square of the mass of the charged particle. Therefore, Bremsstrahlung production for charged particles usually are negligible for heavy charged particles, but they are for electrons, they are not. So when we ever want to characterize the energy lost by heavy charged particles, Coulomb scattering, collisional losses, this would be sufficient to describe the loss of energy of a heavy charged particle, a proton or alpha particle, and so on. But when we deal with electrons and we want to talk about or deal with the stopping power of electrons, then we cannot neglect, in this case, the energy lost through Bremsstrahlung, and therefore the stopping power for electrons needs to be defined through collisional interactions or collisional stopping power and radiating stopping power. The collision stopping power, it's basically inelastic collisions between the charged particle and an orbital electron. And when this happens, so the atom can be ionized. So an energy could be transferred from the charged particle to an orbital electron. And this energy is sufficient such that the orbital electron is going to leave the atom, and leaving the atom to be ionized. And also, maybe that energy was not really enough for the electron to fully leave the atom, but it can actually move this electron to a higher energy state, and therefore the atom becomes excited in this case. Atomic ionization and excitations, they result in collision energy losses experienced by the incident energy electron and are characterized by the collision ionization, or sometimes called ionization stopping power. So just to summarize, we have radiative stopping power. This characterizes or is characterized by the radiation stopping power. And we have the collisional. الصوت بيقطع ولا كويس الصوت؟
لا تمام يا دكتور.
Okay. And we have collision stopping power that basically characterizes inelastic collisions between the charged particle and the orbital electrons. I was planning to go through the derivation, but I felt that it's not really a good. I mean, there are more important things than just deriving this long formula. But essentially, just to give you some history, background history, actually, Niels Bohr was actually the first to derive the mass collision stopping power for a heavy charge particle. And he used it using some classical approach, and he came up with this large formula here that we will talk about it more, inshallah. One parameter that is visible, or it's actually part of this equation, this expression, is the I. This is the mean ionization and excitation energy for the medium. So just so that there is no confusion, this is small z, this is the charge of the charged particle. So if you have a proton, this will be 1. If we have an alpha particle, this will be 2. This is the small z. And the capital Z is the Z of the absorbing medium. So if an alpha particle, for example, or a proton is going through, let's say, lead, then the small z would be the charge of the charged particle. Alpha particle, this would be 2. And the capital Z, this will be the Z of the medium. That would be lead, which is H2. So the mean excitation ionization potential, this corresponds to the minimum energy. So imagine, just so that we understand what's going on, this charged particle, as it's traversing medium, okay, it can actually give energy to the orbital electrons. But we have to remember that these orbital electrons, they're actually bound to the atom. So there has to be a minimum energy that this charged particle can actually give to the orbital electrons in order to transfer energy. Otherwise, no energy will be transferred to this to the orbital electrons. And this, of course, each electron has its own binding energy and so on. So this is an average. This is a mean excitation or ionization potential. This, you have to think of it, is basically the minimum energy that could be transferred on average from the charged particle to orbital electrons. Okay. If electrons were not bound, then the minimum energy would be 0. But since they're bound, then okay, there has to be a cutoff. Below that, no energy on average could be actually transferred to these orbital electrons. It is actually determined experimentally by trying to get from experiments and fitting the data to, for example, simple equations. It cannot be derived from basic principles. So this is an experimental value.
Sorry, Doctor, I have a question. So this mean energy, it's the minimum energy for the particle to interact with the bounding electrons.
No, with an atom, with a medium. Okay, not with a single electron, but with a medium. If we're talking about with a specific orbital electron, then we need to know what's the binding energy of that electron, and what's based on that we can determine what is the minimum energy. But we're talking about now for a medium. In an atom, we don't have a single electron.
Atom.
Yeah, we have many electrons there, and each electron will have its own minimum requirement in order to get energy from the charged particle. So this is an average quantity.
It's not necessarily enough to kick the electron. It's just
not necessarily. No, not necessarily.
Okay, thank you. Thank you, Doctor.
Because remember, when energy is transferred to orbital electrons, either it could be ionization or it could be through excitation. Okay? Now for heavy charged particles, so I think I have it somewhere here just so that I deleted the slide, but I removed it somewhere. Yes. So if we look at this slide here, I removed it at the end. This is actually the collisional stopping power. It's given by or could be expressed in this simple formula, where there is a constant here, something that depends on the charge of the particle, and Z/A. This is related to the medium, and then the beta is the velocity related to the velocity of the particle, and then this parameter, when Bohr derived the stopping power formula classically, he found that this parameter is given by this factor here, and this is the classical derivation, but then Betha introduced quantum mechanics into the derivation, and all what he found, instead of having the square root, we have actually no square root here, so there is a factor of 2 that comes out, and then Betha said, okay, let's introduce relativistic mechanics as well as quantum mechanics. And then he expanded on this formula, found even something more complex. And then later on, they found that actually there needs to be some corrections to the formula derived by Betha. Fano corrections, he has what's called the shell correction and the density corrections that we will talk about. But this is just to give you a form, like a history of the derivation of the stopping power. It went through different stages. So this is for heavy charged particles. This is the classical formula. And then this is now what we accept today. This is the Betha formula. This includes quantum mechanics. as well as relativistic mechanics. It's a long formula here, but two factors that are added. These are what's called the Fano corrections. So Betha is actually all the way up to this minus beta squared, and then Fano corrections, he added these two terms. One is called the shell correction, and the other one is called a density correction factor. So for the shell correction, this happens at very low energy. So in the beta formalism, I think that the assumption was that the orbital electrons were stationary. They were not actually orbiting, but in reality, we know that the orbital electrons, they have some velocity while they're in the atom. Basically, these orbital electrons, they will stop participating in energy transfer from the charged particle when their velocity becomes comparable to the charged particle velocity. So if they have roughly the same velocity as the charged particle, then these electrons will not participate. They will not take energy from the charged particle, and that's why it has a negative term here. So if the Betha formula overestimates the stopping power, in reality, the stopping power is less because of this shell correction. This effect causes an overestimate in the mean ionization excitation potential at low energies and results in an underestimate in calculation from the Betha equations. Since so to account for this overestimation, this is the correction factor is C. C is some constant divided by atomic number Z. And usually, and it's very difficult to obtain these corrections. We need a correction for each shell. But since the K shell electrons, they actually have the fastest electrons, then the correction will be actually dominated by corrections due to the K shell electrons. So this is why it's often addressed as the K shell correction instead of a shell correction. And usually it will be labeled by C sub K divided by Z. And and in this case, that since it's the dominant correction factor, then corrections for higher shells are usually ignored in these values. So the correction term C over Z is a function of two things. It's a function of the absorbing medium, so the medium, and also it's a function of the charged particle velocity. Remember, it's a correction term that is related to the velocities of the orbital electrons relative to the charged particle velocity. So definitely this correction term will depend also on the charged particle velocity. The bottom line, if we have same medium and we have the same particle velocity, then this correction is the same, whether we have electrons or we have positrons. So for example, a proton and an electron, if they're traveling with the same speed, same velocity in the same medium, then the shell correction will be the same for both. The other correction factor is called the density correction, and this accounts for the polarization or a density effect in the condensed medium. I don't fully understand this density correction factor, but what as an explanation is that when we have atoms in the medium, they are ionized. So then we have some sort of a polarization, an electric field. And this could actually affect electrons and adjacent atoms from actually how they're going to interact with the charged particle. The bottom line is that for heavy charged particles, this density correction is important only at relativistic energies. So when the charged particle energy is very, very high, then these density corrections become important. But at intermediate or at low energies, then these are negligible actually, this density correction effect. For electrons and positrons, however, they play an important role and could not be ignored at all energies. So if you see a formula for a heavy charge particle stopping power formula, and you want to apply it, let's say, at lower energies or intermediate energies, and you don't have data for the density correction factor, then it's not really that important. They're negligible. Yeah.
How can we have a charged particle with low energy? It's like it has to be high to be accelerated, you know? Like
No, you can't. It's energy is related to its velocity.
yeah, but to make it, we're gonna have synchrotron or cyclotron, and this is gonna produce a high.
But I'm not talking about production of the charged particle. This charged particle eventually is going to lose its energy. So
And
as it's traversing media, okay, it's going to lose energy. And then, okay, so what happens there? Should we take the does it matter the density correction or it does not? And even for a proton, even if you have, let's say, a 10 MeV proton, 10 MeV proton, that's not a high energy proton. That's not a relativistic particle. You have to look at the kinetic energy relative to its mass. Okay.
So as I understand from you, like when the charged particle now is moving and losing energy, eventually he will lose. He will become intermediate and he will become low.
But you can actually produce intermediate or a low energy charged particle.
How?
You don't need to necessarily start with a high charged particle energy.
Okay. From by the same synchrotron or cyclotron.
Yeah, still the energies of they might not be relativistic. It depends if you're talking about let's say for therapy, we have a 250 MeV protons produced. Okay.
Yeah.
Compared to the mass of the proton, this is still I think this is an intermediate range. The mass of a proton is about 1,000 MeV. But if you have a 10 MeV electron, that's relativistic. A 1 MeV electron is relativistic because the mass of electron is 0.5.
So the range is different between each particles. If it's, for example, if carbon is going to be
But I'm not talking about ranges now. I'm just talking about the stopping powers. So we have a stopping power. We have a charged particle that has a specific energy. Okay.
Yeah.
The question is how much energy this charged particle is going to lose, let's say per distance, per centimeter or whatever.
According to his mass. Carbon is different, proton is different, and electron is different.
So the formula for a heavy charged particle, this is the formula here.
Yes.
Okay? And as we're going to show you, it does not depend on the mass of the charged particle. Okay.
So it depends on what? On the velocity.
We're going to look into this. Okay.
Thank you, doctor.
So that's the shell correction, the density correction. So the density correction. So basically, what it means that actually when we have liquid water, the stopping power for liquid water is actually less than the stopping power for vapor. This is the density correction factor. See, for liquid, this is actually from NIST for electrons. This is for liquid and for vapor. And if we go back to the formula, so this is a negative, okay? It's a negative minus the density correction. So that's why the stopping power for water liquid is actually less than the stopping power for vapor. Okay. So let's look at these dependencies.
Yes.
No.
Is less or more? Because here in curve it looks more.
Yes, this is the density correction, right?
Yeah.
Okay, so for liquid it is higher than vapor.
Yeah.
صح?
In formula, yeah, but you mean in formula it will be less.
So we're talking about the effect on the stopping power now.
Okay.
Okay, so the larger this value, then the smaller will be the stopping power, right?
Okay.
So let's look at the dependence of stopping power on, let's say, on the charged particle. So in this long formula, this small z, this is the charged particle charge, the charge of the charged particle. So the collision stopping power, this means that is proportional to z squared. It's proportional to the charged particle square of the charge of the charged particle. Okay, so we expect, for example, alpha particles, because they have a mass of 2, that their collision stopping power to be somehow, let's suppose the other parameters are remain the same, then it's going to be 4 times that of protons. If you have, like Muhammad wants the carbon ions, carbon ion has 6, okay? So imagine how large will be the collision stopping power in comparison to protons or to alpha particles. What about the particle velocity? Velocity, that's related to the particle kinetic energy. So we look at this large formula, then we see, okay, we have a beta here, and we have here a bunch of betas here in the formula. So for intermediate energies, this factor, this is going to be negligible. And essentially we can say, okay, this collision stopping power, then it is going to be 1 over beta squared. This means as the particle velocity increases, we would expect that the collision stopping power to decrease, to be lower. So the higher the charged particle energy, the lower is actually 1 over beta squared. Yes, this is at low energies. We're talking about at low energies or intermediate energies. What happens then if we go to the relativistic energies, when we go to very high energies? Well, this beta then, since we're relativistic, this parameter beta square is very close to 1. So the dependence on the collision stopping power will not be on this beta square, but this factor then will affect actually the collision stopping power. It turns out that this factor, as beta increases, as we approach the relativistic energies, this beta is 1. Okay, that's a constant, doesn't matter. But 1 minus, so, and this is 1. So this becomes a small number. That means we would expect that this collision stopping power to increase with the kinetic energy. Okay, let me go back again. So if we're going into relativistic ranges, beta square is very close to 1. Okay, it saturates. So it doesn't matter if it's 0.99 or 0.995. It's not really a big problem there. So this factor beta square and this beta square, these are essentially almost 1. And this beta square is also almost 1. But 1 minus beta square, this will become a very small number. As beta approaches 1, this is going to be smaller and smaller. So the ln of the reciprocal of this is going to increase. That's why at relativistic energies, we are going to see a slow increase of the collision stopping power with kinetic energy. How about the mass of the particle? Surprising or not surprising, okay, actually the collision stopping power does not depend on the mass of the incident particle. So we're talking about protons or alpha particles. It is really the Z that really distinguishes or makes a difference in the collision stopping power. But the mass has no effect. And when you have to think of it, this is a Coulomb interaction. So it's the force that will depend on the charge of the particle. It does not depend on the mass of the particle. That's why the collision stopping power does not depend actually on the particle mass. How about the medium? So the medium, what do we have? What's remaining? We have Z over A. So that is the electron density of the medium. And then we have also the mean ionization excitation energy. So Z over A, as Z increases, remember this is something we have to always remember. As Z increases, Z over A slowly decreases. So the maximum value is going to be 1 for hydrogen, helium, 3, it is 0.67. And then for all elements, roughly 0.5. But actually, if we go to higher Z materials, the number of neutrons is actually going to be larger than the number of protons. So Z over A is going to be, will decrease with increasing Z. So it is proportional to Z over A. That's the important thing. Thus, with increasing Z, we would expect that the collisional solving power to slowly decrease with Z. How about for the mean ionization excitation potential? It is going to decrease with I. So if when I increases, the slim will decrease, so the collisional stopping power is going to decrease. But I increases with Z. So if you go back, so this is I. As Z increases, I increases. So what we expect then, that with I, we would expect with Z, I is going to increase, and therefore this, the collisional stopping power is going to decrease. Make sense? So this is the mass collision stopping power. This is a plot for protons, the mass collision stopping power. This is typically how the curve of a mass collision stopping power looks like for heavy charged particles. This is the intermediate range. Remember when we said with increase with increasing energy, the stopping power decreases as 1 over beta squared. This is here where the intermediate range is. So as the energy increases, the collisional stopping power decreases in this intermediate range. But in the relativistic range, we said what happens, it's going to slowly increase. And this is now here where we're starting to see the relativistic range. The stopping powers are now going to slowly increase with the energy. Again, when we look at Z, what happens is higher Z, we have lower collisional stopping power. Okay, so this is the slide here. So with the depends on the medium. So in both here, this and the I, both of them will make the stopping power decrease with Z. And this is what we're seeing in the curve. So protons, here is carbon, aluminum, copper, and lead, and the stopping power is always decreasing along all energies. How about for light charge particles? Light charge particles, so these are electrons and positrons. It turns out actually well, it's a complex formula again. But electrons and positrons, they don't have the same collisional stopping powers. This is the equation for both, and here is the factor, this F plus or minus. So for electrons, then F of tau is given by this relationship, this formula, and F of for positrons is given by even a longer expression here. So tau is just the energy, the kinetic energy divided by the mass of the electron. So now the charged particle that is ionizing the medium is a light charged particle. It is an electron or a positron. The stopping power is not the same as that for a heavy charged particle. The formula that we have shown before, a few slides before, that was a heavy charged particle. So that applies to protons, to alpha particles, and so on. But now for electrons, the formula is a little bit different. And also electrons and positrons, the stopping power of the collision stopping power differs between the two. This is here a plot of the collisional stopping power for electrons. And again, they have the same behavior. We have an intermediate range, at this intermediate energies. Roughly, it's a 1 over beta squared. Something similar to this and then beyond that, then it starts to slowly increase with increasing energy. But again, as Z increases, what we're seeing that the collision stopping power actually decreases. So water has a higher collision stopping power compared to aluminum, higher than lead. Okay, similar to what we have seen for heavy charge particles. Now, the radiation stopping power, remember we said radiation stopping powers, they characterize stopping powers for electrons. Heavy charge particles, the Bremsstrahlung produced is very, very low, negligible. So this is usually, we don't actually have a radiation stopping power for heavy charge particles. But for electrons, yes, we do have that. And the reason is the Larmor relationship, the 1/m² dependence. So if we have a proton and an electron, the mass of a proton is 2,000 times larger than the mass of an electron. So the amount of Bremsstrahlung, both of them, they have the same charge. Okay, and imagine if they are also the same acceleration or same velocity. Everything's the same, except that the masses of the two particles are different. Then for a proton, the amount of Bremsstrahlung or the power of Bremsstrahlung emitted is going to be 1/4 million times smaller than that for an electron. And this is why, and proton is the lightest, let's say, heavy charge particle. Okay, so it just has a proton. Imagine an alpha particle, or even heavy ions, it's going to be even much, much less. So usually we don't actually, or we ignore the radiation losses for heavy charge particles. And this is why this formula is only for electrons. So the radiation stopping power can be expressed by a certain, by this formula here. This is the fine structure, 1/137. This is the classical electron radius. Z, capital Z, is the charge of the medium, is Z of the medium. Okay, and electrons, of course, the Z for electrons is 1. And NA/A, we have here, this is the kinetic energy of the charged particle. Sorry, this is the total energy. So this is basically the sum of the rest mass energy plus the kinetic energy. This should be ET here. And then we have this parameter here. It's a B radiative. This is a slowing, varying function of the Z of the medium, the absorber, as well as on the kinetic or the total energy of the electron. So here, this is the radiative parameter, P rad. If we're in the non-relativistic range, it's basically a constant 16 divided by 3. And then if we want to include relativistic effects, or at the, relativistic range, then this is the kinetic energy is roughly equal to mc². It's a complicated power series. High relativistic, so when the kinetic energy is much larger than the rest mass energy of the electron, but it's still lower than a certain parameter here, then this P rad is given by this formula. And then at extreme relativistic, when the kinetic energy is even more than this, then we have it's given by this formula here. So obviously at non-relativistic, this is B rad is independent of, it does not depend on the absorbing medium, but at higher relativistic, again, I think here, yeah, well, here depends on the, here it does not depend also on the Z of the medium, but I see here in the extreme high relativistic, it depends on the Z of the medium. So the radiative stopping power, it is proportional to the electron kinetic energy. If we go back to the formula, so this is the formula, it is proportional to the kinetic energy here, this ET. As well as on the atomic number Z. So if we go to the formula, So here we have a Z squared, but then why are we saying it's depends only on Z of the medium, not Z squared? Because we have on the denominator here, we have an A. So Z squared over A, we can take one of the Z's, we take it the ratio Z over A, we say, okay, Z over A is almost constant. We does not really change much in medium. So that makes that the collisional stopping power then depends on Z. This is often a tricky question I give to students, that I put the formula, it's a Z squared, and I ask, okay, proportionality of the radiative stopping power, it actually depends on Z, it does not depend on Z over A, Z squared. So these three curves, these represent the radiative stopping powers. And we see something different now here. This is lead, water, and aluminum. So it depends on Z. As Z increases, the radiative stopping powers, there is a typo here, is going to increase. It's proportional to Z, not Z squared. Okay. What we see is that as the energy increases, we see that the radiative stopping power will increase. And if we go to even higher energies, then that stopping power, radiative stopping power, could actually be higher than the collisional stopping powers. So Brahmacharya production through radiative losses is more efficient at higher energy, higher energy electrons, and for a higher atomic number absorbers. So now we know, for example, why when we use targets, X-ray targets, we prefer to use high Z material. We could use low Z material, okay? But we are not going to get as much Brahmacharya when we do that. So we could have, for example, a carbon target. Let's say we have an X-ray tube, we could have a carbon target. We are going to get X-rays. But then most of the energy that we spend to accelerate the electrons will be actually dissipated into heat. Okay? But if we replace the target with high Z material, for example, tungsten, then we're going to get much, or the fraction of energy that is converted to Brahmacharya is going to be higher, and it's going to be actually Z proportional to Z. So tungsten, Z is 74, and carbon is 6. So roughly, we're going to have 74 divided by 6 more X-rays when we do that. The same situation happens at megavoltage range, although there are some other factors that are taken into consideration. That's why targets of a LINAC are not necessarily made from a pure tungsten target, but they could have an intermediate, or they could have copper also as a layer for that. Because there we're thinking also of the spread of the Brahmacharya, at which angles they are going to be produced. So that's a different topic. But in general, we want to produce X-rays. This is why we want to have high Z materials. Also, when we want to shield, for example, let's say we have a beta source, a radioactive material that has a beta source. It's not wise then to use actually high Z material to shield. It is actually better to use a low Z material to shield. Because when these betas are emitted from the radionuclide, they're going to interact with the shielding. So if the shielding material is a low Z, that means, okay, the collisional stopping powers, or the energy of these beta particles are actually being spent more on collisions. We're going to get Brahmacharya, but it's going to be very, very small. Now, if we replace this low Z material with a high Z material, what we're doing is, okay, we are increasing the amount of Brahmacharya that is produced by the beta particles when they interact with the shielding material. And of course, then we have to deal with shielding of the photons. So it would be best, for example, to have an inner surface or an inner material of shielding, a low-Z material, any plastic would do. Okay, and then we have probably, because still that plastic can produce X-rays, then what we do after that is we have some lead shielding in order to shield for the X-rays that are produced by the beta particles. Make sense? So now, based on the physics, we start to think, we start to know how things should work or how we should do things. We have also this concept of a linear energy transfer. This is usually, I mean, the term that this is usually used in is in radiobiology. Or sometimes it's actually used in radiation, for radiation protection. So when you define the quality of a beam, then that would be defined through this term called the linear energy transfer. I think it's something, it's like the linear stopping power. So the LAT usually, by the way, I did not mention this, the SI unit. So the mass stopping powers, their units are typically given in MeV, centimeter squared per gram. So that would be collisional stopping powers, radiator stopping powers, and obviously the total stopping power. So it's energy multiplied by area divided by mass. The SI, or not the SI unit, sorry, the typical unit. The SI unit would be actually joules, meter squared per kilogram, but usually the typical unit that is used in our field is going to be MeV, centimeter squared per gram. And this is where they actually, so in radiation biology, they have this definition of low LET radiation. These are radiation that has low linear energy transfer. I'm not sure what the cutoff is, but anyway, X-rays, gamma rays, X-rays, and electrons, they all have a low LET. The only exception is very low energies of electrons. They have a 10 keV LET, and this comes from here. Okay, so as we go to very low energies, you see the stopping powers, and thus the LET, they're going to be higher. And we have here examples of high LET radiation. These are extreme, very low electrons, 1 keV. And then we have neutrons, protons, carbon ions, and heavy ions. So they lose about carbon ions, they lose 160 keV per micrometer as they traverse medium. So the charged particles, one characteristic that they have different from photons is that charged particles, they do have a range as they enter the medium. So when a charged particle, so imagine we have a heavy charged particle incident in the medium, what's going to happen? Okay, it's going to lose energy. That energy lost will be characterized by the stopping power. So it loses energy, and it will continue to lose its energy, until at the end it have lost all of its energy, and it reaches a certain depth in medium. This is called the range, or more precisely, we can call it the continuous the range with the continuous slowing down approximation. Essentially, continuous slowing down approximation means that this charged particle is not scattered in the medium. It does not actually change its direction. And this is pretty much the case for when we have heavy charged particles. So protons, alpha particles, and so on, as they traverse medium, they're essentially interacting. Remember, collisional interactions, they're interacting with the orbital electrons. So the orbital electrons, they will not, very hard for them to deflect or to change the direction of the heavy charged particles. So the range of this discharge particles essentially is going to equal to the range, assuming the continuous slowing down approximation. However, when we're dealing with electrons, so as an electron enters, electrons can be heavily scattered in the medium. So the range of the path of an electron is not going to be a straight line. It's going to go like something like this, a path like that, and go deep and then come back, and then only when it reaches this point, it has lost all of its energy. So this is the deepest point that the electron has reached. This is called the range of the electron. But the range for electrons is definitely going to be less than the range, assuming the continuous slowing down approximation. So continuous slowing down approximation, imagine if this is a thread, imagine we are just taking this, we're looking at the length or the distance traveled by this electron, not the depth in medium, but actually the depth, the distance that this electron has actually traversed in the medium. That is the range, assuming continuous slowing down approximation. So for large charged particles, the range is less than the CSDA, whereas for heavy charged particles, they're both of them are approximately the same. So now we come to this term or definition of a radiation yield. Imagine we have a 1 keV, 1 MeV, let's say electrons. Whenever we talk about radiation production, we're talking about large charged particles. So it doesn't make sense to have a radiation yield for a proton or for a heavy charged particle, because we said that radiation interactions, these are negligible compared to the collisional interactions. But for electrons, these are significant. So the definition of the radiation yield is that it is the fraction of the initial kinetic energy that is emitted as photons. I'll give an example. So imagine we have a 1 MeV electron entering medium or interacting with medium. Then it's going to, part of its energy is going to be lost into collisions. Let's say at the first few micrometers, part of its energy is going to be lost in collisions, and part of it will be emitted as radiation. Now, when it loses its energy, it's going to interact again in the next micrometer. Again, it's going to lose part of that, its energy to collisions, and part of it as radiated. So if I want to know at that particular instant how much energy is lost due to radiation and how much due to collisions, we're going to use the collision stopping power, provided we know the energy of the electron at that instant. But now if I ask you, let's repeat this calculation, and at the end, I want you to get out what is the total energy of Brahms-Charag emitted by the electron from its initial kinetic energy until it stopped, compared to its initial energy. Of course, the energy of the Brahms-Charag, the total energy of Brahms-Charag emitted cannot exceed, its kinetic energy. Doesn't make sense, right? So that fraction, or that fraction is what we call the radiation yield. So it is defined as the fraction of the initial kinetic energy that is emitted as photons through the slowing down process of the particle in the absorber until it stops. We're looking at all the photons or all radiation, well, we're looking at all photons emitted from its initial kinetic energy until it stops. So the photons that are emitted will be through Brahms-Charag, also characteristic X-rays. Remember, when it undergoes collisional interactions, it's going to ionize atom, excite atom, and then the atom will start to relax. When this happens, relaxation, the atom could actually emit characteristic X-rays. So that energy is also part of that radiation yield. And the last thing is, this is particular for positrons. So positrons, when they undergo in-flight annihilation, not when they stop. So when they stop, that's fine, no problem. That's not part of the radiation yield. But radiation yield is, it has a kinetic energy. We want to know how much of the particle kinetic energy was actually emitted in the form of photons. So a positron, if it slowed down, did not interact through Brahma until it lost all of its energy, that then when it annihilates, it will emit the two annihilation photons, 0.5 and 1. 0.5 and 1, these are not part of the radiation yield. Okay? Only in-flight annihilation. Only if it undergoes in-flight annihilation before, or annihilation before it actually loses its energy, then we have to see how much of that energy converted to photo or carried out by the annihilation photons, and that will be part of the radiation yield. This is the figure from the past, the Brahms angular distribution about the theta max and the angle, just to explain, to show that when we have a single interaction at low kinetic energies, the maximum intensity is actually will be at 90 degrees, and as the electron energy increases, then the maximum intensity will be at a lower angle, theta max. And this explains, for example, why X-ray targets are built in such a way, why linear targets are built in such a way. We also have this concept. This is an important concept, will allow us to look into cavity theories in the next lecture, and how to calculate doses and so on. This is the mean collision stopping power. So when a particle traverses medium, let's say an electron, or in this case, we can actually apply it also for a heavy charged particle. We want to know, so at each energy, as it's moving, at each energy, we know it has it's going to lose energy through collisions, and that is governed by the mass collision stopping power. So if we want to calculate what is the mean collision stopping power, one trick we could do is, okay, we know the initial energy of the particle, and let's remove any energy lost to Brahms-Chaland and divide that by the range of the particle. Okay. So in this, that's why this formula could also be applied to heavy charged particles, because the radiation yield for heavy charged particles is basically 0. Okay, but for electrons, this radiation yield will depend on the kinetic energy. So for example, if we want to calculate what is the mean collision stopping power, let's say for a 1 MeV electron. So along its path from 1 MeV all the way until it stopped, what is the mean collision stopping power? Okay, so the energy of the electron is 1 MeV. We come back, we look at this curve here. We need to know the absorber. Suppose the absorber, let's say, is carbon. So 1 MeV, we look at the radiation yield. The radiation yield, this is roughly around 0.3, for example. Okay. Let's go back. Okay, the formula. So we take that value for the radiation yield, and then we look at what is the range. There are tables actually. If you look at NIST, they have some data. Let's probably I can show you. They have a very nice database. You can go there and look at. So here, E star is electron stopping powers, P star, and this is proton stopping powers. And A star, I think this is for alpha stopping powers. So let's look at E star. And this is here, this is the database. So we can have this for elements. We can have it for the medium. So here, for example, let's look at water liquid, and let's submit this. So this is the collision. This is the total stopping power, actually. Okay. And here we have the table. We have the collisional, we have the radiative, and the stopping powers as a function of kinetic energy. This is the CSDA range. Okay, and this is here the radiation yield. So if we can actually use this table to calculate immediately what is the mean energy, let's say for mean collision or stopping power for 1 MeV electrons. We will go here to, let's say 1. So we have the formula. What we need, the energy, which is 1 MeV. We need the radiation yield, which is this here. And then we need the range. So the range is this value. Again, the last column here, this is the delta. This is the density effect parameters. So I actually copied the data for liquid and for vapor because there is a water vapor, and plotted the density effect parameter, and this is what I showed you earlier. So anyway, this is a table. We have the stopping power. Let's call this instantaneous stopping power. We want to know 1 MeV. What is the stopping power for at 1 MeV? Then we will go at 1 MeV and pick up the value, collisional and radiative. But now we want to know what is the mean stopping power of the electron until it loses all of its energy. So it's basically some sort of like an integration, okay? We have to track down this electron, and we can calculate that mean stopping power using the range, continuous slowing down approximation range, as well as the radiation yield from this table. This formula will come handy in the next lecture. Finally, I want to talk about restricted collision stopping power. This is important when we want to deal with dosimetry, when we want to, for example, know the dose in a specific region in media. And that's why this concept is important. The massive collision stopping power can overestimate the dose. The reason why is if we look at, imagine we have a primary electron, and this is our region of interest. We want to know the dose, or what's the energy deposited in this region of interest. Okay? So this is the primary electron. It entered the region of interest. As it enters, it's going to undergo collision interactions. Okay. For those, of course, radiative interactions, that's energy carried out away. So now collision interactions. We have secondary electrons that are being produced. So these are electrons, these are orbital electrons within the medium. And energy is going to be transferred to these orbital electrons. It can happen that we can have a hard collision between an electron and orbital electron, or an energy transfer to a secondary electron. But this secondary electron, then it's going to leave the region of interest. So if I want to calculate the dose accurately, this energy is actually going to be carried out of the region of interest. So we have to somehow exclude that. We don't want that in determining the dose. The collision stopping power, yes, this electron, this is the amount of energy that this electron has spent in creating these secondary electrons. So that's the energy lost by the primary electron. That's not a problem. But if some of these electrons leave our region of interest, and I'm interested in calculating the dose, the energy deposited in that region of interest, we have to exclude that. We have to remove them. We should not include them. That's why when estimating the dose, If we use the collisional stopping power, we are going to overestimate the dose, because we are calculating the energy that is transferred to all of these secondary electrons without really removing the energy that is carried away out of this region of interest. Okay. Now, the region of interest, what's the size of this region of interest? This will depend on the problem we're looking at. For example, if we are looking at a cell, then what we need to do, we have, okay, the size of this region of interest, it's in a micrometer. So probably we need to go and look back, what is the range of electrons? So if we look at here, so it's a micrometer, then this is in, so suppose it's less than a meter. This is still, the energies I think are too high. You see here, even at one, this is 10 MeV, 10 keV. The range is about 0.2 millimeters. The range of an electron, a secondary electron that has 10 keV, this is its range. Definitely, if this was produced in a cell, then this electron is actually going to go outside of the cell. So if I want to calculate what's the dose to the cell, and I'm using the collisional stopping powers, I'm overestimating. I'm going to overestimate, because some of the up to, I think usually what they do is they go down to 100 keV. That's estimated as the range. If we're dealing with, for example, ionization chambers or something in air, so usually electrons, 10 keV, that would be a good value to use. So we look at, for example, a 2 millimeter air, roughly a 10 keV of electrons. It can actually, more than that, this electron is going to leave our region of interest. So although this is for next lecture, but imagine we have a primary electron and it's entering an air, let's say a chamber. Okay. Any secondary electron produced with energy greater than 10 keV, it can actually leave our air volume. So if I want to calculate the dose in air, then, and I use the collisional stopping power, I'm going to overestimate actually the dose there. So the restricted stopping power is a way to exclude these things. So this is why it was introduced, is the concept of restricted mass collisional stopping power, usually denoted as L with a delta here, has been introduced to address this issue by including the delta rays. These energetic electrons that can leave the region of interest, usually they're called the delta rays. Okay, so with delta rays, energies exceeding a suitable threshold value. So essentially, we're selecting a restricted stopping power with a delta, let's say it's 10 keV. When we do that, we're saying, okay, secondary electrons produced with energy exceeding 10 keV, they're going to leave, and thus we have to remove them from the stopping powers that we're going to use. So the choice of the energy threshold, this will depend on the problem at hand. It depends if we're looking at the dose in a cell, or we're looking at those, let's say, in air, or so on, for chambers and so on. So we have to select an appropriate delta that represents the problem. Okay. Obviously, delta must not exceed the maximum energy. So for example, we know for an electron, a 1 MeV electron, the maximum energy that could be transferred is going to be 0.5, half of its kinetic energy. It doesn't make sense. Then we say, okay, we're going to restrict collision stopping power. We're going to exclude any secondary electron produced with energy greater than 0.5, because actually no secondary electron will be produced with an energy greater than 0.5. Okay, so in order to have some meaningful meaning to this restricted stopping power, the delta that we select should not or must not exceed the maximum energy transfer. So for electrons, the maximum energy equals to the electron energy divided by 2. For positrons, the maximum energy that could be transferred is equal to the kinetic energy of the positron. And then if I have a heavy charge particle, the maximum energy transfer is given by this relationship here, where beta is actually the velocity of the heavy charge particle. So here is a plot. We have 3 stopping powers. One is the collisional. Sometimes it's called the unrestricted collisional stopping power. Unrestricted meaning any secondary electron produced by the charged particle or by the primary charged particle. The assumption is that it's not going to leave our region of interest. And here, this is now the restricted collisional stopping power, where we have a cutoff energy of delta of 100 keV. And the last curve here, the dashed curve, we have delta equals to 10 keV. So let's look at 10 MeV. If you have a 10 MeV electron, okay, the amount, if we use the unrestricted stopping power, then the energy, it's this value. The secondary electrons, the energy of the secondary electrons can be from 0 all the way up to 5 MeV. But the assumption is that in our region of interest, all of these electrons, even this 5 MeV electron, is still not going to leave our region of interest. Now, when we restrict the stopping powers, let's say to 100 keV, okay, what we're doing here now is that we're using stopping power where we're excluding, we're saying all electrons that are produced with energy above 100 keV, those, they will carry the energy out of the region of interest. So the primary charge particle still loses that energy, but that energy will not be deposited locally in our region of interest, because the assumption is that secondary particles with energy greater than 100 keV, they are going to carry that energy away from our region of interest. So that's why it is lower, because we will have electrons produced with energy higher than 100 keV, but these are actually depositing their dose outside of our region of interest. So that's why we're excluding that. And if we make it even tighter, we make the delta 10 keV, then again, we see that the restricted stopping power is actually going to decrease, because more of the electrons are actually carrying away energy away outside of this region of interest. So since the energy transfers to secondary electrons are limited to 0.5 keV, the unrestricted mass collisional stopping power and restricted mass collisional stopping power are identical for a given kinetic energy. For electrons lower than or equal to 2 keV. What does this mean? It means, now, if we have, let's say, at 200 keV. So imagine my primary electron is, its energy is 200 keV. The maximum energy that it can transfer is 100 keV. Okay? Essentially, the unrestricted and the restricted collisional stopping power for 100 keV below this energy, below that, they're going to be identical. They're going to be the same. And if we have an electron, if my primary electron has an energy of 20 keV, okay. So imagine this is, I'm talking about this energy of the primary electron. If this is 20 keV, the maximum possible energy of secondary electrons is going to be 10 keV. And therefore, the collisional, the unrestricted and the restricted collision stopping power, 10 keV, they are going to be identical, lower than that energy. For a given kinetic energy, so if the energy is greater than this 2 delta, then the smaller is delta, the larger is the discrepancy between unrestricted and restricted stopping powers. So if we're looking at energies, let's say at 1 or let's say at 100, at 10 MeV, basically the smaller delta is, the smaller will be the restricted collision or stopping power. And this is what we're seeing for 100 keV is larger than for delta equals to 10 keV. For a given delta and E equals greater than 2 delta, the larger is the kinetic energy, the larger is the discrepancy between the unrestricted. And this difference between the unrestricted and restricted, okay, so here, remember, we said for 200 keV, below this energy, the unrestricted and restricted, they should be the same. As we increase the energy, we start to see that they're not the same. There is going to be a deviation. And basically, as we increase the energy, the deviation is going to increase. It's going to be larger and larger and larger. Okay? So this is what I have for today, the lecture for today on stopping powers. It's an important concept that we are going to need in for our next lecture. Next lecture, inshallah, I will be talking about cavity theories, inshallah. So any questions?
I do have a comment, Doctor, not a question, if you allow me. It has been a fantastic sessions. It covers a lot of variety of topics which needed, to be honest. But I'm suggesting that because we covered photon interaction with matter, we covered light particle interaction with matter, positron and electron, we cover heavy ion and carbon. How about we do neutrons? Can you do?
I could give a lecture on neutrons, not a problem. We'll see.
So
I will see maybe next session I will do cavity theory or I will do neutrons. Neutrons is not I will need a session probably, or even less than a session. I'm
yeah,
not an expert on interactions of neutrons, but that's something we can add.
because it's not this like it's neutron, no charge, and it's gonna be more. I don't know, but I will really appreciate it if we can have a session of neutrons.
Inshallah.
By that we can.
So I'll see. Maybe at the end we can talk about neutrons. Inshallah.
Thank you, Doctor.
I'm gonna start recording this time.